Hi, my name is Bill Kinney and I'm a professor at Bethel University. And this is the first of a series of videos that I'm making on calculating integrals that arise in arc length calculations for parametric curves. That's kind of a mouthful. Perhaps you are doing this as part of a multivariable calculus or calculus 3 class, maybe even a calculus 2 class. We're going to focus on doing the calculations. I'm assuming that you know the formula in such a situation, this thing right here. I'm not going to explain it at all. We're just going to focus on actually doing integrals that arise because sometimes they're pretty tricky integrals. That's why I'm making this video series. So what we have here is we're given a smooth, meaning differentiable, parametric curve, call it C of t, that's got two coordinates, x of t and y of t, and we are considering this curve over a certain time interval from t equals a to t equals b. The goal here is to find what's called the arc length of the curve from t equals a to t equals b. That's the traditional name, and I'll stick with that as the title, but let me just say that, and we'll see with this example perhaps, I'm not sure if I'll get to this in this video, maybe the next one. You'll see that it's actually better described as a distance traveled instead of an arc length, but we won't buck tradition at the moment. So again, here's the formula. You want to integrate the square root of the sum of the squares of the derivatives of the coordinates of your parametric curve, or components if you're thinking of it as a vector. Say that again. Integrate from a to b the square root of the sum of the squares of the derivatives of these coordinates or components of your parametric curve. So that's the formula. We're going to apply it to a specific situation here. Find the arc length of this parametric curve, c of t equals 3t squared as the first coordinate or component, and t squared minus 1 is the second, from t equals 0 to t equals 4, and then we're going to consider that same parametric curve but over a different interval from -4 to 4. I'm not quite sure if I'll have the time to get to that in this video. I'd like to make these videos about 10 minutes each. We'll see how it goes here. So how are we going to do this calculation? Well, let me first just copy and paste this formula downward here. Alright, so there's the formula. And copy and paste again to save some time here. I'm going to go ahead and plug in the derivatives. The derivative of 3t squared, looking up here, is what I put here. That derivative is 6t. The derivative of y of t, which is t squared minus 1, is 2t. And a is 0 and b is 4. So this is the integral we have to do. First, let's simplify it. We can square 6t squared, quantity squared, it will be 36 times t squared. 2t quantity squared will be 4 times the quantity t squared, altogether giving us 40 times t squared. So that's one simplification we can make. What else can we do? Well, we can also separate out the square root of 40, put that out in front as a constant. I also can write 40 as 4 times 10, and the square root of 4 is 2, so ultimately that's a 2 times square root of 10 there. And I could then put a square root of t squared inside here. However, the square root of t squared, what do you think that's equal to? Maybe stop and think. Maybe pause the video. Do you know? Well, it is equal to t when t is positive. However, in general, it's equal to the absolute value of t, like that, because t could be negative. Now, of course, if you look at the integral, it's not in this case, but it's a good habit to get into to replace the square root of t squared, for example, with the absolute value of t, just in case t could range over negative values, which it actually does down further here because we're letting t go from -4 to 4. So this is definitely a good habit, and in fact that's why I picked this example, so that I could highlight that point. This is a fairly easy arc length integral compared to most that we're going to encounter, but we'll start simple and get harder here. Alright, so But now I'll go ahead and get rid of the absolute values in this case, because this thing is being integrated from positive over positive numbers, 0 to 4. Anyway, now it's an easy integral to do. Go ahead and put it on the next line here. Of course, integrating t is going to give you 1/2 t squared. The 2's are going to cancel. We're integrating from t equals 0 to t equals 4. Again, the 2's cancel. We've got that square root there still of 10. And you plug in t equals 4. 4 squared is 16. And subtract what you get when you plug in 0. 0 squared is 0. So we have 16 square root of 10 here. That would be a more traditional way to write it. And that'll be the arc length. I am in a Mathematica notebook, in case you haven't noticed. So we certainly could check that, at least the integral calculation, by being in input mode and going ahead and having Mathematica calculate what we just did here, the integral we just did, square root of 40t squared dt, the unsimplified version. There we go, 16 square root of 10. And I can also approximate that. That previous output can be approximated to be about 50.5964. This section has an animation in it that can illustrate that that seems right. And in fact, this is kind of a nice example. We're going to see that it's actually a straight line, this parametric curve, though not at a constant speed. So that black dot is the point that's moving. The parametric curve is modeling the motion of that black dot. And it's a straight line, even though the coordinate functions x of t and y of t are not linear. You can easily see by eliminating t, for example, by solving x equals 3t squared for t squared is x over 3, and then replacing the t squared here with x over 3 to get y equals x over 3 minus 1 as the equation of this line. But it's because those are nonlinear coordinates, this is not a constant speed. Anyway, but it is straight, and in fact we can calculate the beginning point at the point 0, -1 here, and the ending point when t is 4, let's see, we're going to be at the point 4 squared times, 4 squared is 16 times 3 is 48, and then 15. The point 4815 is the ending point. And then you could actually calculate the length of that curve by using the distance formula. 48 minus 0 squared plus, again, the second coordinate of that ending point was 15, minus -1 squared, and then take the square root. That's the distance formula of that line, and we get the same answer. Alright, I think real quick we can emphasize what happens in this other case. What's the solution in this other case, where we start at t equals -4? There the absolute value is definitely essential. We're integrating the absolute value function here from -4 to +4. Now the one convenient thing that happens here is we can get rid of the absolute value sign because this is actually an even function, the absolute value of t. If you graph it, it looks like a V centered on the y-axis with a point down at the origin. And because of that, it's an even function. We can actually integrate it from 0 to 4 and then just double the answer. So we actually ultimately get double the previous answer. If you didn't quite catch that, you might want to stop the video and rewind and try to catch what I said. I'll say it again quick. The actual integrals from -4 to 4 of this absolute value function, but that's an even function of t, so I can really do the integral of just t from 0 to 4, which is the absolute value of t when t is positive, and double the answer, so I can take my old answer and instead of having a 2 there, I can have a 4, which is going to double our final answer to being 32 times the square root of 10. Watch what happens when we animate this, though. The point starts on the right now, goes toward the left, and then goes back again. So what we're really calculating here is not the literal length of this line segment. We're calculating the distance traveled and that by the point, and that's why it's really better called a distance traveled instead of an arc length. But it is traditional to call it an arc length, but just realize it's better interpreted as a distance traveled.